From the neighborhood to the edge of time, the James Webb Space Telescope challenged our understanding of the cosmos and showed the universe in a way no other telescope in the past could. And in a recent remarkable observation, the $10 billion Infrared Space Observatory has focused on Mercury, which should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. And now, by using powerful telescopes like James Webb, scientists have once again lifted the veil on the secrets of the planet, revealing Mercury is not what we think. Join us as we shed light on the most enduring mysteries of the innermost planet in our solar system. Mercury is the closest planet to the Sun, orbiting at an average distance of about 57.9 million kilometers. With a diameter of just 4,880 kilometers, it is the smallest planet in the solar system, slightly larger than Earth's moon. Despite its proximity to the Sun, Mercury's surface temperatures vary dramatically, ranging from scorching highs of 430 degrees during the day to freezing lows of 180 degrees at night. Mercury's orbit is highly eccentric, meaning it is not a perfect circle, but rather an elongated ellipse. This eccentricity, combined with its rapid orbital period of just 88 Earth days, leads to fascinating orbital dynamics that have intrigued astronomers for centuries. One of the most notable features of Mercury's orbit is its 3-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the Sun. The surface of Mercury is a stark, barren landscape, characterized by numerous impact craters, vast plains, and towering cliffs. The planet's surface bears the scars of a violent history, with craters ranging in size from tiny pits to massive basins hundreds of kilometers across. The largest of these is the Caloris Basin, a massive impact crater over 1,500 kilometers in diameter, formed by a colossal collision with an asteroid or comet billions of years ago. Mercury's surface is also home to a network of long, steep cliffs known as Lobat Scarps. These scarps are thought to have formed as the planet's interior cooled and contracted, causing the crust to buckle and fracture. Some of these cliffs rise as high as 3 kilometers and stretch for hundreds of kilometers across the planet's surface. Despite its barren appearance, Mercury's surface is not entirely devoid of activity. Recent observations have revealed evidence of volcanic activity in the planet's past, with smooth plains and ancient lava flows suggesting that Mercury once had a more geologically active history. However, unlike Earth or Venus, Mercury's volcanic activity appears to have ceased billions of years ago, leaving behind a frozen, lifeless landscape. One of the most puzzling aspects of Mercury is its magnetic field. Mercury is the only terrestrial planet besides Earth to have a global magnetic field, although it is much weaker than Earth's. The existence of this magnetic field was first confirmed by NASA's Mariner 10 spacecraft in the 1970s, but its origin remains a mystery. A planet's magnetic field is typically generated by the motion of molten iron within its core, a process known as the dynamo effect. However, given Mercury's small size and proximity to the Sun, scientists were surprised to find that the planet still has an active dynamo. Theories suggest that Mercury's core may contain a higher proportion of iron than previously thought, or that the planet's core has a unique composition or structure that allows it to sustain a magnetic field. Adding to the mystery is the fact that Mercury's magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern hemisphere, a phenomenon that is not yet fully understood. Some scientists believe that this asymmetry may be due to variations in the planet's core or mantle, while others suggest that it could be a result of interactions between the magnetic field and the solar wind. What's more, unlike Earth, Mercury has no significant atmosphere. Instead, the planet is surrounded by an extremely thin layer of atoms known as an exosphere. This exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, and is constantly replenished by the solar wind, micrometeoroid impacts, and the release of volatile materials from the planet's surface. The existence of Mercury's exosphere was first confirmed by Mariner 10 and later studied in greater detail by NASA's MESSENGER spacecraft. The exosphere is so tenuous that it is barely detectable, with an atmospheric pressure less than a trillionth of Earth's. Despite its thinness, the exosphere plays a crucial role in the planet's interaction with the solar wind and the space environment. One of the most fascinating aspects of Mercury's exosphere is its dynamic nature. The atoms in the exosphere are constantly being stripped away by the solar wind, only to be replaced by new atoms from the surface. This continuous exchange of particles creates a delicate balance that can be easily disrupted by solar activity, leading to fluctuations in the composition and density of the exosphere. Mercury's most striking feature is its unusually large core, which makes up about 85% of the planet's radius. This core is believed to be composed primarily of iron, with smaller amounts of nickel and other elements. The sheer size of Mercury's core relative to its overall size is unique among the terrestrial planets and has led to much speculation about the planet's formation and history. One of the leading theories suggests that Mercury may have once been a much larger planet, with a thick rocky mantle similar to Earth's. However, a giant impact early in the planet's history could have stripped away much of this mantle, leaving behind the dense metallic core we see today. This giant impact hypothesis is supported by the planet's high density and the relative scarcity of silicate materials on its surface. The core of Mercury is also thought to be partially molten, which may explain the planet's magnetic field. But the exact state of the core, whether it is completely liquid, partially solid, or something in between, remains an open question. Understanding the nature of Mercury's core could provide valuable insights into the formation and evolution of the inner planets in our solar system. However, given its proximity to the Sun and the extreme conditions on its surface, Mercury is a challenging planet to study. Mercury has been visited by only 2 spacecraft, NASA's Mariner 10 and MESSENGER missions. These missions have provided the bulk of our current knowledge about the planet, but what is really interesting about Mercury are the things that can't be seen. And now, thanks to incredible research efforts, scientists have finally given us some remarkable clues that could upend our understanding of this enigmatic world. In a groundbreaking revelation, scientists have discovered that Mercury, the innermost planet in our solar system, may harbor salt glaciers that could support life beneath its sun-scorched surface. This discovery is not only a significant leap in our understanding of the planet's geology, but also raises intriguing possibilities about the potential for life in environments once deemed inhospitable. The key to this new discovery lies in the data gathered by NASA's MESSENGER spacecraft, which orbited Mercury from 2011 to 2015. MESSENGER's suite of scientific instruments provided unprecedented insights into the planet's surface composition, magnetic field, and geological history. One of the most surprising findings from MESSENGER's mission was the detection of unusual surface features that suggested the presence of volatile substances, including water ice and salts. Researchers have long known that Mercury's poles contain deposits of water ice, trapped in permanently shadowed craters. These craters, located in the planet's polar regions, are shielded from the sun's harsh rays, allowing ice to accumulate and persist. However, the discovery of salt glaciers has added a new dimension to our understanding of Mercury's polar deposits. Analysis of MESSENGER's data revealed features that resemble glaciers on Earth, but with a twist. These so-called salt glaciers are formed from a mix of salts, such as sodium chloride and magnesium sulfate, and ice. The presence of these salt deposits suggests that, at some point in Mercury's history, liquid water may have been present on the planet's surface and subsequently evaporated, leaving behind these saline features. The formation of salt glaciers on Mercury involves several stages. First, volatile compounds such as water and various salts were likely present in the planet's crust. Over time, geological processes, including impacts and volcanic activity, would have brought these materials to the surface. When Mercury's surface temperatures fluctuated, especially in the shadowed regions near the poles, water ice could have formed and mixed with salts. The persistence of these salt glaciers is indicative of a complex climatic history. The planet's axial tilt is minimal, meaning that its poles receive very little direct sunlight. This, combined with the extremely low temperatures in the shadowed craters, has allowed these glaciers to remain relatively stable over geological timescales. The discovery of salt glaciers on Mercury prompts a re-evaluation of the planet's potential to support life. While the current conditions on Mercury are inhospitable to life as we know it, the presence of salts and ice raises the possibility that microbial life could exist in subsurface environments, similar to how life is hypothesized to survive beneath the icy crusts of moons like Europa and Enceladus. In addition to the presence of water ice and salts, the idea that Mercury once had a more temperate climate further fuels speculation about its potential for life. If liquid water was once stable on the surface, it opens up the possibility that life could have had a chance to develop during that period. Even if no evidence of life is found, these findings can provide valuable insights into the planet's geological history and the processes that shaped its surface. Another remarkable discovery: recent scientific research has unveiled a breathtaking possibility. Mercury might be hiding a treasure trove unlike anything we could have imagined, a diamond layer 15 kilometers thick. To understand how Mercury could host such an incredible deposit of diamonds, we first need to appreciate the planet's unique geological and environmental conditions. As told, Mercury is a planet of extremes. With temperatures fluctuating from a blistering 400 Grad during the day to a bone-chilling 180 Grad at night, the surface is subject to tremendous thermal stress. This temperature variation alone suggests that the planet's surface could be a breeding ground for complex chemical reactions. Additionally, Mercury's lack of a substantial atmosphere, unlike Earth's thick blanket of air, leaves it exposed to the harsh solar wind, a constant stream of charged particles from the sun. These factors combine to create an environment where only the toughest materials can endure. This leads us to the key ingredient in our story: carbon. We all know that carbon is an essential element in the formation of diamonds. Under the right conditions, extreme pressure and temperature, carbon atoms can rearrange themselves into a crystal structure, creating diamonds. On Earth, diamonds are formed deep within the mantle, where pressures are immense. They are then brought to the surface through volcanic eruptions encapsulated in kimberlite pipes. But Mercury's formation and evolution took a different path. Recent studies suggest that Mercury's formation was marked by a cataclysmic event. During the early days of the solar system, a massive impact stripped away much of Mercury's outer layers, leaving it with an unusually large core relative to its size. This event could have also compressed large amounts of carbon deep within the planet, creating conditions ripe for diamond formation. Unlike Earth, where tectonic activity and erosion constantly reshape the surface, Mercury's geological activity is limited. This means that any diamonds formed in its early history could have remained largely undisturbed, accumulating over billions of years to form a thick layer. The idea of a 15-kilometer thick diamond layer on Mercury might sound like science fiction, but it's grounded in solid scientific principles. If Mercury's early history did involve massive impacts and intense pressure, it's plausible that much of the planet's carbon was converted into diamonds. Over time, as Mercury cooled and solidified, these diamonds could have settled into a stable layer beneath the surface. Moreover, Mercury's proximity to the Sun means it has been bombarded with meteoroids for billions of years. These impacts could have further driven carbon deep into the planet's crust, adding to the growing diamond reservoir. Some scientists hypothesize that the upper crust of Mercury could be a mix of regolith and diamond-rich rock, with the diamonds concentrated at deeper levels where pressures were once highest. One might wonder how such an extraordinary claim could be substantiated. The challenge lies in the fact that Mercury is not an easy planet to study. Its proximity to the Sun makes it difficult for telescopes to observe, and sending spacecraft to Mercury presents its own set of challenges. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided a wealth of data that has since been analyzed to offer clues. Messenger's X-ray and gamma-ray spectrometers detected higher-than-expected levels of carbon on Mercury's surface, particularly in certain regions. This carbon, found in the form of graphite, could be the remnant of a once more extensive carbon layer that has since been weathered down by meteoroid impacts and solar wind. If graphite exists in significant quantities, it strengthens the case for diamonds lying beneath, as graphite and diamond are different forms of carbon. Moreover, the high radar reflectivity observed in some of Mercury's craters is another piece of evidence. Radar signals bounce back strongly from highly reflective surfaces, such as ice or metal. However, diamonds are also excellent reflectors of radar waves, meaning that these bright spots on Mercury's radar map could be hinting at diamond-rich areas. Regardless, to fully understand the implications of these discoveries, future missions to Mercury are crucial. The next major mission to Mercury is Bepi-Colombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in October 2018, Bepi-Colombo is currently en route to Mercury, with its arrival scheduled for December 2025. This mission is named after Giuseppe Bepi Colombo, an Italian scientist who first explained the relationship between Mercury's rotation and its orbit around the Sun. Bepi-Colombo consists of two spacecraft, the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA. The two spacecraft will work in tandem to study Mercury's surface, interior, exosphere, and magnetosphere in unprecedented detail. The MPO will focus on the planet's surface and interior, mapping its topography, composition, and geological features, while the MMO will study the planet's magnetosphere and its interaction with the solar wind. One of the key objectives of Bepi-Colombo is to build on the discoveries made by Messenger and answer some of the lingering questions about Mercury. For example, Bepi-Colombo will investigate the origin of Mercury's magnetic field, which is much weaker than Earth's, and is likely generated by a partially molten core. The mission will also study the composition of the planet's surface, including the mysterious hollows, bright, shallow depressions that appear to be unique to Mercury. In addition to its scientific goals, Bepi-Colombo will test advanced technologies that could be used in future missions to Mercury and other planets. For example, the mission's solar electric propulsion system, which uses ionized xenon gas to generate thrust, could pave the way for more efficient space travel in the future. While Bepi-Colombo represents the next significant step in Mercury exploration, scientists are already looking ahead to future missions that could build on its findings. These missions could take various forms, from orbiters and landers to sample return missions, and even human exploration. One of the most exciting prospects for future Mercury exploration is the idea of sending a lander to the planet's surface. A lander would provide an unprecedented opportunity to study Mercury's geology up close, analyze its surface composition, and conduct experiments that are not possible from orbit. For example, a lander could drill into the surface to study the planet's interior structure or deploy instruments to measure the heat flow from the interior to the surface, which could provide clues about the planet's thermal evolution. However, designing a lander capable of surviving Mercury's extreme conditions presents significant challenges. The lander would need to be equipped with a sophisticated thermal control system to protect it from the intense heat of the sun, as well as radiation-hardened electronics to withstand the harsh environment. Additionally, landing on Mercury's surface is no easy feat given the planet's low gravity and lack of atmosphere, which makes it difficult to slow down the descent. Despite these challenges, there have been several proposals for Mercury lander missions. One such proposal is the Mercury Surface Element, also known as MSE, a concept developed by ESA as part of the Bepi-Colombo mission. Although the MSE was ultimately not included in the mission, the concept could serve as the basis for future lander missions. Another proposal is the Mercury Lander Mission concept, developed by NASA's Jet Propulsion Laboratory, or JPL, which envisions a lander equipped with a suite of scientific instruments to study the planet's surface and interior. Another ambitious goal for future Mercury exploration is the return of samples from the planet's surface to Earth. A sample return mission would allow scientists to conduct detailed analyses of Mercury's surface material in laboratories on Earth, providing insights that are not possible with remote sensing or in situ measurements. For example, scientists could study the isotopic composition of Mercury's rocks to learn more about the planet's formation and evolution, or search for traces of volatile elements that could shed light on the history of water on the planet. Designing a sample return mission to Mercury poses several technical challenges. The spacecraft would need to carry a lander capable of collecting samples, as well as a return vehicle to bring the samples back to Earth. The mission would also need to overcome the challenges of operating in Mercury's extreme environment, as well as the difficulties of launching a spacecraft from the planet's surface. Despite these challenges, advances in technology and lessons learned from previous sample return missions, such as NASA's OSIRIS-REx mission to the asteroid Bennu, could make a Mercury sample return mission feasible in the future. While human exploration of Mercury is still a distant prospect, it is not entirely out of the realm of possibility. Advances in space technology, such as nuclear thermal propulsion and advanced life support systems, could one day make it possible for humans to visit Mercury and conduct scientific research on the planet's surface. Human missions to Mercury would likely be similar in scope to the Apollo missions to the Moon, with astronauts landing on the surface for short durations and conducting experiments before returning to Earth. Human exploration of Mercury would offer several unique opportunities for scientific research. For example, astronauts could conduct geological surveys of the planet's surface, study its magnetic field and interaction with the solar wind, and search for signs of past or present water. Additionally, human missions to Mercury could serve as a stepping stone for future exploration of other planets in the inner solar system, such as Venus or Mars. The future missions to Mercury have the potential to revolutionize our understanding of the planet and its place in the solar system. By studying Mercury's surface, interior, atmosphere, and magnetosphere in greater detail, scientists hope to answer key questions about the planet's formation and evolution, its geological history, and its interaction with the Sun. One of the key scientific objectives of future Mercury missions is to understand the planet's unique composition. Mercury has a much higher metal content than any other planet in the solar system, with a large iron core that makes up about 85% of its radius. This unusual composition has led scientists to propose several theories about Mercury's formation, including the possibility that the planet was once much larger and lost much of its outer layers in a giant impact. Future missions could provide the data needed to test these theories and determine the true origin of Mercury's composition. Another important objective is to study Mercury's magnetic field and its interaction with the solar wind. Unlike Earth, Mercury's magnetic field is weak and highly variable, with frequent reconnection events that create intense bursts of radiation near the planet's surface. By studying these phenomena in greater detail, scientists hope to gain insights into the dynamics of planetary magnetic fields and their role in protecting planets from solar radiation. Future missions could also shed light on the history of water on Mercury. Although the planet is thought to be too hot for liquid water to exist on its surface, MESSENGER discovered evidence of water ice in permanently shadowed craters at the poles. BepiColombo and future missions could study these ice deposits in greater detail, potentially revealing clues about the sources of water in the inner solar system and the history of volatiles on Mercury. Finally, future missions to Mercury could help answer fundamental questions about the formation and evolution of the solar system, and by extension, offer clues about the conditions that led to the formation of Earth and other terrestrial planets. One of the most intriguing aspects of Mercury is its unusually high metal content. The planet has an iron-rich core that accounts for about 85% of its radius, which is proportionally much larger than Earth's core. This composition suggests that Mercury experienced a different formation and evolutionary history compared to the other terrestrial planets. Understanding why Mercury is so metal-rich could shed light on the processes that influenced planetary formation in the early solar system. There are several hypotheses about Mercury's high metal content. One theory suggests that Mercury might have formed from material that was metal-rich from the beginning, possibly as a result of the Sun's early influence. Another hypothesis proposes that Mercury originally had a silicate-rich mantle similar to Earth's, but a massive impact during its formation stripped away much of this mantle, leaving behind a metal-rich core. Studying Mercury in detail could help scientists determine which of these scenarios is more accurate, providing insights into the conditions that existed in the inner solar system during its formation. Mercury is the only other terrestrial planet besides Earth that has a significant magnetic field, although it is much weaker than Earth's. The presence of this magnetic field suggests that Mercury has a partially molten outer core, which generates the field through the dynamo effect. By studying Mercury's magnetic field, scientists can learn more about the planet's core dynamics and how its magnetic field has evolved over time. Understanding Mercury's magnetic field could also provide clues about the early magnetic history of Earth. Earth's magnetic field is crucial for protecting our planet from solar and cosmic radiation, making it a key factor in the development and sustenance of life. By comparing Earth's magnetic field with Mercury's, scientists can gain a better understanding of the factors that influence magnetic field generation in terrestrial planets and how these fields evolve. This knowledge could also help scientists predict the future behavior of Earth's magnetic field, which is currently weakening. Mercury's surface is heavily cratered, similar to the Moon, but it also has unique features such as large cliffs or lobate scarps that run for hundreds of kilometers. These scarps are thought to have formed as Mercury's core cooled and contracted, causing the planet's surface to shrink and buckle. The presence of these scarps suggests that Mercury's geological history is still active, albeit at a much slower rate than on Earth. Studying Mercury's surface features can provide insights into the planet's geological history and the processes that have shaped its surface over billions of years. For instance, understanding the formation of lobate scarps can help scientists learn more about the thermal evolution of Mercury's core and mantle. This, in turn, can offer clues about the thermal histories of other terrestrial planets, including Earth. Mercury also has regions known as smooth plains, which are believed to be the result of ancient volcanic activity. The presence of these plains suggests that Mercury had a more geologically active past than previously thought. By studying the volcanic history of Mercury, scientists can learn more about the planet's internal heat generation and how it has changed over time. This information could be valuable for understanding the volcanic history of Earth and other terrestrial planets, as well as the role of volcanism in planetary evolution. Mercury has a tenuous atmosphere, or exosphere, composed mainly of hydrogen, helium, oxygen, sodium, and potassium. Unlike Earth's thick atmosphere, Mercury's exosphere is constantly being replenished by particles from the solar wind, surface interactions, and outgassing from the planet's interior. Studying Mercury's exosphere can provide valuable information about the interactions between the solar wind and planetary surfaces. The study of Mercury's exosphere is particularly important because it offers a unique opportunity to observe how a planet's surface and atmosphere interact with the solar wind. Since Mercury is so close to the Sun, it experiences much stronger solar wind conditions than Earth. By understanding how Mercury's exosphere responds to these conditions, scientists can gain insights into the processes that shape planetary atmospheres in general. This knowledge can also be applied to Earth, helping scientists better understand how our planet's atmosphere interacts with the solar wind, and how this interaction has influenced Earth's evolution. Mercury's unique characteristics challenge many existing models of planetary formation. Traditional models suggest that terrestrial planets formed from the gradual accumulation of planetesimals in the protoplanetary disk. However, Mercury's high metal content, weak magnetic field, and unusual surface features suggest that its formation involved processes that are not fully explained by these models. Studying Mercury in greater detail can help scientists refine these models and develop new theories about planetary formation. For example, understanding why Mercury has such a large iron core relative to its size could provide insights into the role of giant impacts in planetary formation. Similarly, studying Mercury's magnetic field and geological history can help scientists develop more accurate models of how terrestrial planets evolve over time. Mercury offers a unique opportunity for comparative planetology, the study of planets by comparing their properties and histories. By comparing Mercury with Earth, scientists can identify similarities and differences that provide insights into the process that shaped both planets. For instance, both Mercury and Earth have metallic cores and magnetic fields, but the differences in their sizes, compositions, and geological histories can help scientists understand the factors that influence planetary evolution. One key area of comparative planetology is understanding the role of size in planetary evolution. Mercury is much smaller than Earth, which has significant implications for its thermal evolution, magnetic field generation, and geological activity. By studying these differences, scientists can learn more about how a planet's size influences its evolution and what this might mean for Earth. Another area of interest is the study of planetary atmospheres. While Earth has a thick atmosphere that supports life, Mercury's exosphere is extremely thin and constantly influenced by the solar wind. Comparing these two atmospheres can provide insights into the factors that determine atmospheric retention and composition, which are crucial for understanding the conditions necessary for life. Mercury's proximity to the Sun and its unique characteristics make it a valuable target for studying the early solar system's evolution. The planet's high metal content, weak magnetic field, and unusual surface features suggest that it has experienced processes that are not fully understood and that may have been more common in the early solar system. By studying Mercury, scientists can gain insights into the processes that influence the formation and evolution of the solar system as a whole. For example, understanding Mercury's formation and evolution could provide clues about the distribution of materials in the protoplanetary disk, the role of giant impacts in planetary formation, and the thermal histories of terrestrial planets. These insights could also help scientists better understand the conditions that led to the formation of Earth and other habitable planets. In short, while Mercury is a small planet with a big story to tell, its unique characteristics make it a key target for understanding the formation and evolution of the solar system, including Earth. By studying Mercury's composition, magnetic field, geological history, and exosphere, scientists can gain valuable insights into the processes that shaped our planetary neighborhood. These insights can help refine existing models of planetary formation and evolution, providing a clearer picture of how Earth and other terrestrial planets came to be. As we continue to explore Mercury, we are likely to uncover even more secrets about the early solar system and the forces that shape the world we live on today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. The James Webb Space Telescope is the most significant advancement in human endeavor toward unraveling the mystery of the cosmos. More than just a telescope, James Webb is humanity's most potent eye in the sky, providing the ability to observe the universe billions of years back and hopefully unlock the key to the cosmos's evolution and provide answers to some of the most fundamental questions asked by humanity. But when James Webb used its powerful and sensitive infrared eye to peer back into the beginning of times, what it unveiled was nothing short of revolutionary and potentially catastrophic for our understanding of the cosmos. The revelations James Webb brought forth would set the scientific community on edge, igniting fierce debates and existential questions about the very fabric of our universe.
Thing is wrong. We may have to revise our theory of the creation of the universe.
Join us as we dig deep into what James Webb really saw at the dawn of time. To understand what James Webb is seeing, we first need to revisit the concept of the beginning of time as described by the Big Bang theory. According to this theory, the universe began as an extremely hot and dense point, often referred to as a singularity, approximately 13.8 billion years ago. This singularity contained all the mass and energy of the universe in an infinitesimally small space, and for reasons still not fully understood, it began to expand. This expansion marked the birth of the universe, as space itself began to stretch, and time as we know it began to flow. In the first fractions of a second after the Big Bang, the universe underwent a rapid expansion known as cosmic inflation. During this brief period, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. As the universe continued to expand and cool, energy was converted into matter through processes described by quantum mechanics and Einstein's theory of relativity. In the first few minutes after the Big Bang, conditions were right for the formation of simple atomic nuclei, primarily hydrogen and helium, in a process known as nucleosynthesis. These elements would later serve as the building blocks for stars and galaxies. As the universe expanded and cooled further, gravity began to take over, pulling matter together to form the first structures in the universe. Small density fluctuations in the early universe, amplified by gravity, led to the formation of dark matter halos, within which gas could cool and condense to form stars. These early stars, known as population 3 stars, were massive and short-lived, playing a crucial role in enriching the universe with heavier elements through supernova explosions. Over time, these stars began to cluster together under the influence of gravity, forming the first galaxies. Galaxies are the basic building blocks of the universe, vast systems containing billions of stars along with gas, dust, and dark matter. The formation of galaxies was a key step in the universe's evolution, as they provided the environments in which stars could form, evolve, and die, creating the complex chemical elements needed for planets and life. In the centers of galaxies, clouds of gas and dust collapsed under gravity, to form stars. Around some of these stars, the remaining gas and dust coalesced to form planets. Our own solar system, for example, formed about 4.6 billion years ago from a cloud of gas and dust left over from previous generations of stars. The Sun formed at the center of this cloud, with the remaining material forming the planets, moons, asteroids, and comets that make up our solar system. But while most of us strongly believe that the Big Bang is the best way to explain how the universe started and how it changed over time, the fact is that this model, while powerful, does not provide a complete account of cosmic history. Instead, it leaves unanswered questions about the nature of dark matter and dark energy, the asymmetry between matter and antimatter, and critically, the details of the universe's dark ages, the period after the Big Bang, but before the first stars ignited. One of the most significant gaps in the Big Bang theory involves the formation of the first stars, known as population 3 stars. The formation of the first stars marks one of the most significant epochs in cosmic history, the transition from the Dark Ages to a universe filled with light and structure. This event, known as cosmic dawn, is shrouded in mystery, primarily because the first stars are thought to be fundamentally different from the stars we observe today. The first stars formed from the primordial hydrogen and helium gas left over from the Big Bang. Unlike stars today, which form in regions enriched with heavier elements, metals, the first stars were born in an environment devoid of such elements. This absence of metals profoundly affected their formation and characteristics. One of the central mysteries surrounding the first stars is their mass. Theoretical models suggest that, in the absence of metals, the cooling processes in the early universe were inefficient, leading to the formation of extremely massive stars, with masses ranging from tens to hundreds of times the mass of the Sun. These massive stars would have had short lifetimes, burning through their nuclear fuel rapidly and ending their lives in violent supernovae or collapsing directly into black holes. Despite their importance in cosmic history, detecting the first stars has proven to be a formidable challenge. These stars formed at such an early epoch that they are extremely distant, and their light has been redshifted to wavelengths that are challenging to observe with current technology. Moreover, because they were so massive and short-lived, they would have rapidly ended their lives in powerful supernova explosions, leaving behind little direct evidence. One of the key challenges in detecting population 3 stars is the sheer distance involved. The light from these stars has traveled for over 13 billion years to reach us, and during that time, the universe has expanded, stretching the light into the infrared part of the spectrum. This means that traditional optical telescopes, like the Hubble Space Telescope, are not well suited for detecting them. However, the advent of the James Webb Space Telescope has provided a new window into this distant past. As the most powerful space telescope ever built, James Webb is equipped with a suite of advanced instruments optimized for infrared observations. This capability is crucial for studying the early universe, where the light from distant galaxies and stars has been stretched into the infrared part of the spectrum due to the universe's expansion. James Webb's design also allows it to peer through dust clouds that obscure many regions of space from visible light telescopes like Hubble. This is particularly important for studying the early stages of star and galaxy formation, as these processes are often shrouded in dense clouds of gas and dust. That's why one of James Webb's primary science goals is to observe the first galaxies and stars, probing the epoch of Ryanization and beyond. By capturing light from objects that formed just a few 100 million years after the Big Bang, the telescope can provide direct evidence of the universe's earliest structures. This, in turn, will help answer fundamental questions about how the first stars formed, how they influenced their surroundings, and how they led to the complex cosmic web of galaxies we see today. And as expected, since its launch, James Webb has already begun to revolutionize our understanding of the early universe. One of its most significant achievements has been the discovery of the earliest galaxy ever seen. Named JADES GS Z14-0, the galaxy formed at least 290 million years after the Big Bang and contains stars that have been bursting into life since an estimated 200 million years after our universe began. Spotted by James Webb's Near-Infrared Spectrograph, or NIRSpec instrument, the mysterious origins and rapid development of the stars has opened up some fundamental questions about how our universe came to be. Astronomers aren't certain when the very first globules of stars began to clump into the galaxies we see today, but cosmologists previously estimated that the process began slowly within the first few 100 million years after the Big Bang. Current theories suggest that halos of dark matter, a mysterious and invisible substance believed to make up 85% of the total matter in the universe, combined with gas to form the first seedlings of galaxies. 1 billion to 2 billion years into the universe's life, these early protogalaxies reached adolescence, forming into dwarf galaxies that began devouring one another to grow into ones like our own. But discoveries made by James Webb confounded this view. In February 2023, a group of astronomers analyzing data from the telescope discovered a group of 6 gargantuan galaxies aged between 500 to 700 million years after the Big Bang that were so massive they were in tension with 99% of cosmological models. The light from JADES GS Z14-0 is similarly puzzling. In the new research, the light detected by NIRSpec finds its origins in an enormous halo of young stars surrounding the galaxy's core, which have been burning for at least 90 million years before the point of its observation. The galaxy is also crammed with unusually high quantities of dust and oxygen, which suggests its history of starbirth and death may be even longer. Interestingly, this finding shows that ultra-bright galaxies in the early universe are not just the product of active black holes greedily gobbling up matter, as is often assumed to be the case. The new observations show that runaway star formation is also a viable explanation for the surprising brightness of these ancient galaxies. So how did galaxies like JADES GS Z14-0 produce so many stars so quickly? Answers to this cosmic mystery remain elusive, but it's unlikely they will break our current understanding of cosmology. Instead, astronomers are toying with explanations that include the earlier-than-anticipated appearance of giant black holes, supernova feedback, or even dark energy to understand why these ancient stars were able to form so rapidly. Fascinatingly, in addition to discovering early galaxies, James Webb has provided critical insights into the formation of the first stars, known as Population 3 stars. While direct observation of the very first stars remains elusive, James Webb has detected signatures of their presence through the observation of early galaxies. The ultraviolet light emitted by these stars ionized the surrounding hydrogen gas, contributing to the reionization of the universe. By studying the spectra of these galaxies, the telescope has identified the chemical fingerprints of the first stars, providing evidence that these primordial objects played a significant role in shaping the early universe. Webb's observations have also hinted at the possible existence of Population 3 star clusters, which would be some of the oldest and most massive star-forming regions ever observed. These clusters would have been responsible for producing the first heavy elements in the universe, setting the stage for the formation of later generations of stars and galaxies. Another area where the Webb telescope has made groundbreaking discoveries is in the study of black holes during the cosmic dawn. Supermassive black holes, with masses millions to billions of times that of the Sun, are known to exist at the centers of many galaxies. However, their origins and how they grew so massive in such a short period after the Big Bang have been long-standing mysteries. James Webb has detected signs of supermassive black holes in some of the earliest galaxies, providing clues about their formation. One theory is that these black holes formed from the collapse of massive primordial stars or dense star clusters, which then rapidly accreted gas and merged with other black holes to grow in size. The presence of these black holes in early galaxies also has implications for galaxy formation. It suggests that black holes and galaxies may have grown together, influencing each other's evolution. The intense radiation and outflows from these black holes could have regulated star formation in their host galaxies, shaping the development of cosmic structures. Moreover, data obtained by James Webb also have provided valuable data on when and how reionization occurred. By observing the light from distant galaxies and quasars, James Webb has measured the amount of neutral hydrogen in the early universe, offering insights into the timing and duration of reionization. Interestingly, Webb's findings suggest that reionization may have been a more complex and extended process than previously thought. Rather than occurring rapidly over a short period, reionization might have proceeded in stages, with different regions of the universe being ionized at different times. This challenges the traditional view of a uniform, simultaneous reionization, and opens up new avenues for research into the interactions between early galaxies, black holes, and the intergalactic medium. What's notable, the insights provided by James Webb are not just of interest to astronomers. They have broader implications for our understanding of the Big Bang theory itself. By providing a clearer picture of the universe's first billion years, James Webb helps fill in critical gaps in our knowledge, offering new data that can be used to refine and test cosmological models. For instance, Webb's observations of early star and galaxy formation challenge existing models of how quickly structure formed in the universe. If star formation began earlier than expected, this could have implications for our understanding of dark matter and its role in cosmic evolution. Similarly, the detection of heavy elements in early galaxies suggests that the first stars may have been more massive and short-lived than previously thought, potentially influencing models of stellar evolution and nucleosynthesis. Moreover, Webb's ability to study the intergalactic medium, the diffuse gas that fills the space between galaxies during the epoch of reionization, provides new insights into the nature of dark matter and dark energy. By mapping the distribution of this gas and its interaction with early galaxies, the telescope can help constrain models of how dark matter clumps together to form the large-scale structure of the universe. Interestingly, as of now, the James Webb Space Telescope is still in its early stages of operation. In other words, its full scientific potential is yet to be realized. Regardless, the discoveries it has already made are a testament to its transformative power. As James Webb continues to observe the early universe, it will undoubtedly provide more answers to the fundamental questions about the cosmos's origins and evolution. In the coming years, the observatory is expected to make significant contributions to our understanding of exoplanets, star formation, and galaxy evolution, in addition to its work on the early universe. Its ability to observe in the infrared will also allow it to study objects that are currently hidden from view, such as planets forming around young stars or the cores of galaxies enshrouded in dust. Moreover, Webb's discoveries will likely inspire new theories and models, prompting a deeper investigation into the nature of the universe. As we continue to explore the cosmos with James Webb, we may uncover new phenomena that challenge our current understanding, leading to a more complete and nuanced picture of the universe's history. By that time, no doubt, the question of whether it was time to overthrow the government would have been discussed countless times. After all, the Big Bang, as told, despite its success in explaining many aspects of cosmology, is not without its gaps and unresolved questions. These gaps challenge our understanding of the universe's origins and have driven ongoing research and exploration in modern cosmology. One of the most profound issues with the Big Bang theory is its treatment of the universe's initial state. The theory describes the evolution of the universe from a fraction of a second after the Big Bang onward, but it does not extend to the actual moment of creation, nor does it address the cause of the singularity itself. This leaves a gap in our understanding, a gap that science, as it currently stands, cannot fill. At the heart of the Big Bang theory lies the concept of a singularity, a point where the density of matter and energy becomes infinite, and the laws of physics as we know them break down. Singularities are deeply problematic in physics because they represent a breakdown of our understanding. In the context of the Big Bang, the singularity is a point where our current theories, namely general relativity and quantum mechanics, cease to be applicable. General relativity, which describes the force of gravity and the structure of space-time, predicts the existence of singularities under certain conditions. However, these predictions indicate that at a singularity, space-time becomes infinitely curved, and physical quantities such as density and temperature become infinitely large. In other words, the very fabric of the universe would be infinitely warped, and the physical laws that govern everything from the motion of planets to the behavior of subatomic particles would no longer hold. Quantum mechanics, which governs the behavior of particles at the smallest scales, also fails to describe what happens at a singularity. Quantum theories suggest that at extremely small scales, the fabric of space-time becomes dominated by quantum fluctuations, leading to a highly chaotic and indeterminate state. However, when combined with general relativity, these theories produce nonsensical results, such as infinite densities and curvatures. The existence of singularities in the Big Bang theory therefore suggests that our current understanding of the universe is incomplete. It implies that a more fundamental theory, possibly one that unifies general relativity and quantum mechanics, is needed to describe the true nature of the universe's beginning. In response to the limitations of the Big Bang theory, several alternative theories have been proposed to explain the origins of the universe. These theories attempt to address the question of what came before the Big Bang, or to describe a universe without a beginning at all. One such theory is the idea of a cyclic universe, where the universe undergoes infinite cycles of expansion and contraction. In this model, the Big Bang is not the beginning of the universe, but rather a transition from a previous cycle of contraction. The universe contracts into a singularity-like state, then rebounds in a new Big Bang, leading to a new cycle of expansion. This theory avoids the problem of a singularity by proposing that the universe never actually reaches infinite density, but instead undergoes a bounce at extremely high densities. Another theory is the multiverse hypothesis, which suggests that our universe is just one of an infinite number of universes that exist in a larger multiverse. According to this theory, different universes can have different physical laws and constants, and our universe may have originated from the collision or interaction of two or more universes within this multiverse. In this context, the Big Bang is simply a local event within a much larger and more complex cosmic structure. There is also the possibility that the universe had no beginning at all. Some theories propose that the universe is eternal, with no origin point. These models often involve modifications to the laws of physics to allow for a universe that has always existed in some form, without requiring a singularity or a moment of creation. For example, some versions of quantum gravity suggest that time itself may not exist in the traditional sense at the earliest moments of the universe, making the concept of a beginning meaningless. The mystery of the universe's beginning also raises profound philosophical and theological questions. If science cannot provide a complete answer to the question of the universe's origin, can these questions be addressed through other means? From a philosophical perspective, the question of the universe's beginning touches on the concept of causality, the idea that every event must have a cause. The Big Bang suggests a moment when the universe began, but what caused the Big Bang? This leads to a classic philosophical problem, the problem of the first cause. If every event must have a cause, then what caused the first cause? This line of reasoning can lead to an infinite regress, where each cause requires a preceding cause, or it can suggest the existence of a cause that itself is uncaused, an idea that some equate with the concept of God. Theological perspectives often address the question of the universe's beginning by invoking the idea of a divine creator. Many religious traditions teach that the universe was created by a deity or deities who exist outside of time and space and are not subject to the physical laws that govern our universe. This view holds that the universe had a purposeful beginning, brought into existence by an intelligent and transcendent being. However, the idea of a divine creator also raises questions. If the universe requires a cause, then what caused the creator? Some theologians argue that God is a necessary being, existing beyond the constraints of cause and effect, while others suggest that the nature of God is fundamentally mysterious and beyond human understanding. In the end, the question of the very first beginning of the universe remains one of the deepest and most enduring mysteries. While science has made tremendous strides in explaining the evolution of the universe from its earliest moments, it has yet to provide a definitive answer to what, if anything, came before the Big Bang. The singularity at the heart of the Big Bang theory points to the limits of our current understanding, suggesting that a more fundamental theory is needed to fully describe the universe's origin. At the same time, the mystery of the universe's beginning invites philosophical and theological inquiry, raising questions about the nature of causality, the existence of a first cause, and the possibility of a divine creator. These questions, like the scientific questions, remain unresolved, leaving us with the humbling realization that the origins of the universe may forever remain beyond our grasp. Another significant gap in the Big Bang theory is the horizon problem. According to the theory, regions of the universe that are separated by vast distances should not have had enough time to come into thermal equilibrium due to the finite speed of light. However, the cosmic microwave background radiation, the afterglow of the Big Bang, is remarkably uniform across the sky, with only tiny fluctuations. This uniformity suggests that distant regions of the universe must have been in causal contact with each other in the early universe, which contradicts the predictions of the standard Big Bang model. The horizon problem challenges our understanding of the early universe. It suggests that there must have been some mechanism that allowed distant regions to communicate and reach equilibrium faster than the speed of light would allow. This discrepancy led to the development of the inflationary theory, which proposes that the universe underwent a rapid exponential expansion in the first fractions of a second after the Big Bang. While inflation theory addresses the horizon problem, it is not yet fully integrated with the rest of the Big Bang framework and raises its own set of questions. Closely related to the horizon problem is the flatness problem, another gap in the Big Bang theory. Observations of the universe show that it is remarkably flat, meaning that the geometry of space is close to Euclidean. A flat universe has a delicate balance between the density of matter and energy and the rate of expansion. If the universe were slightly more or less dense, it would have quickly diverged from this flatness, leading to a very different cosmic evolution. The flatness problem is puzzling because the Big Bang theory does not inherently predict this fine-tuned balance. Without an explanation, this flatness seems coincidental, which is unsatisfying to cosmologists. The inflationary theory, again, provides a potential solution by suggesting that the rapid expansion of the early universe would have stretched its geometry, making it appear flat today. However, as with the horizon problem, inflation is an add-on to the Big Bang theory rather than a fully integrated component. One of the most profound gaps in the Big Bang theory concerns the nature of dark matter and dark energy, which together make up about 95% of the total energy density of the universe. The Big Bang theory, as it was originally formulated, accounted for the observable matter and energy in the universe, but did not predict the existence of these mysterious components. Dark matter is thought to be responsible for the gravitational effects observed in galaxies and clusters of galaxies that cannot be explained by visible matter alone. Its presence is inferred from its gravitational pull on visible matter, but it does not emit, absorb, or reflect light, making it invisible and difficult to detect directly. Despite extensive research, the exact nature of dark matter remains unknown. Dark energy, on the other hand, is even more mysterious. It is believed to be responsible for the accelerated expansion of the universe, a phenomenon that was discovered in the late 1990s. Unlike dark matter, which exerts a gravitational pull, dark energy seems to have a repulsive effect, driving galaxies apart at an increasing rate. The Big Bang Theory does not explain the origin or nature of dark energy, and its discovery has led to a re-evaluation of the theory. These gaps highlight the limitations of the Big Bang Theory in describing the full contents of the universe. While the theory provides a framework for understanding the observable universe, it does not account for the vast majority of its energy content, leaving dark matter and dark energy as significant open questions in cosmology. Another unresolved issue in the Big Bang Theory is the baryon asymmetry problem. The theory predicts that equal amounts of matter and antimatter should have been created in the early universe. However, our universe is overwhelmingly composed of matter, with very little antimatter observed. This asymmetry is puzzling because when matter and antimatter meet, they annihilate each other, producing energy. If equal amounts had been created, they should have annihilated each other completely, leaving behind a universe filled with only radiation. The existence of a matter-dominated universe suggests that some process must have created an imbalance between matter and antimatter in the early universe. Various theories have been proposed to explain this asymmetry, including mechanisms that involve slight differences in the behavior of particles and antiparticles. However, none of these theories have been confirmed, and the baryon asymmetry problem remains an open question in cosmology. The Big Bang Theory provides a broad outline of how the universe evolved from a hot, dense state to its current form, but it leaves significant gaps in our understanding of how the first stars and galaxies formed. According to the theory, the early universe was a nearly uniform soup of particles, with tiny fluctuations in density. Over time, these fluctuations grew under the influence of gravity, eventually leading to the formation of the first stars and galaxies. However, the details of this process are not fully understood. For example, the exact conditions under which the first stars, known as population 3 stars, formed are still unclear. These stars are believed to have been massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been produced. The formation of the first galaxies, and how they evolved into the complex structures we see today, also remains an area of active research. Recent observations by the James Webb Space Telescope have begun to shed light on these early stages of cosmic evolution. James Webb's ability to observe the universe in infrared wavelengths allows it to peer back in time to see the first galaxies forming just a few 100 million years after the Big Bang. These observations are helping to fill in some of the gaps in the Big Bang Theory by providing direct evidence of the early universe's structure and composition. As James Webb continues its mission, it is expected to make even more groundbreaking discoveries that will further our understanding of the early universe. Future observations will likely uncover more about the nature of population 3 stars, the formation and growth of the first galaxies, and the role of black holes in cosmic evolution. James Webb will also explore the transition from the cosmic dawn to the later stages of cosmic history, including the formation of more complex structures like galaxy clusters and the chemical enrichment of the universe. By studying the light from the earliest stars and galaxies, James Webb will help us piece together the story of how the universe evolved from a hot, dense state to the vast, complex cosmos we see today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Mercury should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference of nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. A thin atmosphere, a magnetic field, and a stash of volatile compounds still persist on Mercury, features that scientists usually associate with planets that are larger and farther away from the Sun. While new observations from the last few decades have given scientists good cause to revise their opinion of Mercury.
Mercury is basically a big ball of metal surrounded like a tiny bit of rock. And the major question is, why? Why is it like this when the rest of the planets aren't?
Its secrets remain. But now, by using powerful telescopes, scientists have stumbled upon these secrets. But what they found is so weird. There is something moving that they never saw anywhere else. Such a stunning revelation could even lead to crucial missions to reveal a terrifying truth about our universe. Join us as we shed light on the dark shadow that Mercury has kept under wraps. Named for the fleet-footed Roman messenger god, Mercury is the closest planet to the Sun, zipping around our parent star at an average of 36 million miles away. However, Mercury's orbit is not a perfect circle. The planet can pass as close as 29 million miles and as far away as 43 million miles. Living up to its name, Mercury is the fastest planet in the solar system, speeding along at about 29 miles per second and completing each orbit around the Sun in just 88 Earth days. Mercury is also the smallest planet in the solar system, measuring just 3,032 miles wide at its equator. That makes it only slightly larger than Earth's moon. Because Mercury is so small and so close to the Sun, it is the most elusive of the 5 planets that are visible to the naked eye. You can only catch Mercury at dawn and dusk, and it usually does not rise far above the horizon. But that's not the only time the tiny planet makes an appearance. Because of its position in the solar system, Mercury passes between Earth and the Sun 13 times each century in an event known as a transit. During a transit of Mercury, observers on Earth can see the planet in silhouette as it seems to sweep across the Sun's disk. Since ancient times, people observing the heavens have noticed that the naked eye planets sometimes appear to move backward, briefly shifting from their usual eastward motion to a westward path across the sky. This retrograde motion is an illusion created when one planet moves faster in its orbit than another, so that it catches up to and passes the slower world. For observers on Earth, Mercury is in retrograde about 3 to 4 times a year. If you could watch the skies from the surface of Mercury, you would sometimes catch the rare sight of the Sun in retrograde. As Mercury makes its closest approach to our smoldering star, its orbital speed exceeds its rate of rotation on its axis. That means someone standing on Mercury would see the Sun start to rise, then briefly set, then rise again, all within the same day. Like the other planets in the solar system, Mercury was born about 4.5 billion years ago, condensing from the swirling ring of dust and gas left over from the Sun's formation. The small planet cooled very quickly, contracting enough within the first billion or so years to prevent magma from escaping through the outer crust and ending geologic activity such as volcanism on the surface. And while Mercury may be small, it's hefty. Although its diameter is barely larger than the Moon's, Mercury is over 4 times as massive as Earth's natural satellite. In fact, Mercury is the second densest planet in our solar system, after Earth. The planet's extreme density comes from the fact that it has a large iron core that makes up about 60% of the planet's volume. In contrast, Earth's core by volume is only about 15%. The abnormal internal structure has spawned several theories on Mercury's birth. Scientists think that perhaps early Mercury's outer layer was boiled away by the sun or scattered by solar winds. Or perhaps the young planet could have been struck by a large impactor that stripped away most of the softer outer layer, leaving behind its sturdier heart. Since part of the mantle and crust are still present today, this suggests that the collision may not have been a head-on smack, but a glancing brush that preserved some of Mercury's original layers. The first mission to Mercury, Mariner 10, was launched in 1973 and found that Mercury still sustains a magnetic field. The discovery came as a shock to the scientific community, who had assumed that such a small planet would have rapidly cooled, and its insides would have congealed, thereby losing any means of magnetism at the global scale. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field is off-kilter. The magnetic South Pole doesn't sit on the geographic South Pole. Instead, it is buried almost at the center of the planet. The magnetic field offers a glimpse of the planet's interior and a snapshot of its history, hinting at how far the whirling insides have decelerated over billions of years. Due to its proximity to our star, Mercury is hot. If we're being quantitative, it's actually extremely hot. As the closest planet to the Sun, it completes an orbit in just 88 Earth days, achieving a maximum temperature during the day of a whopping 427 degrees at its hottest equatorial locations. Mercury rotates very slowly, so its night side spends a consecutively long time in the dark, shielded from the Sun. During those times, it gets down to just minus 173 degrees. That low temperature is incredibly cold, and far colder than any known naturally occurring temperatures here on Earth. But despite being the closest planet to the Sun, Mercury is not the hottest planet in the solar system. Venus is about twice as far from the Sun on average as Mercury is, taking about 225 Earth days to orbit the Sun. It also rotates even slower than Mercury, spending more than 100 consecutive Earth days at a time bathed in sunlight, and then an equal amount of time in darkness. And yet, when you measure the temperature of Venus, there's a surprise. Venus is the same temperature at all times, day or night, at an average of 462 degrees, making it even hotter than Mercury. This strange occurrence did more than just puzzle astronomers when they first discovered it. It mortified them. Venus wasn't large enough to generate its own heat, and yet it was hotter at Venusian midnight than at Mercurian high noon. Why's that? Well, that is because of the main difference between the two worlds. Venus has a very substantial one that's some 190 times as thick as Earth's is, but Mercury, instead of a substantial atmosphere, has such a thin atmosphere that it doesn't really qualify as an atmosphere. Instead, scientists call this wispy layer of gas an exosphere, where the gas is so rarefied that it hardly registers a pressure reading. Mercury takes a constant beating from the Sun, so its exosphere has to regenerate itself from the surface. Since the 1980s, astronomers have detected in Mercury's exosphere atomic sodium, potassium, and calcium, metals with strong emission signals that can be observed all the way from Earth with telescopes. These metallic elements are not usually thought of as gases, but they find their way into Mercury's skies by dint of solar particles and meteorites striking the planet's surface. Solar winds gouge the resulting exosphere, and the interactions between the gases and sun-flung particles fashion a 15-million-mile-long glowing tail behind Mercury. This tail lengthens and shrinks seasonally, depending on Mercury's proximity to the Sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear in the sky as a faint orange glow, as if the heavens were illuminated by sodium streetlights. A planet perched right at the Sun's maw shouldn't harbor any water, let alone ice, or so researchers thought. But in the 1990s, scientists at Goldstone in California and the Arecibo Radio Telescope in Puerto Rico directed a stream of radar signals toward Mercury. The teams were astonished to observe two brightly reflective spots at the poles, likely icy deposits. In 2012, MESSENGER confirmed that the ice at Mercury's North Pole was frozen water. Laser measurements on board identified carbon-rich material on the surface that insulates an ice pack underneath. Mercury has managed to cling on to its water because it has pockets in permanent shadow. Relative to its orbit around the Sun, the planet spins perfectly upright, like a soldier at attention facing a commanding officer. That means the impact craters near the poles have insides that never see any daylight. Temperatures within these divots dip below -173 degrees Celsius, close to the temperature where nitrogen gas liquefies. It's cold enough that ice can be stable over geological timeframes. And as on most other rocky planets, the water on Mercury probably came from asteroids that crash-landed onto the surface. This water hides in Mercury's craters, untampered with since primordial times. On other terrestrial planets in the solar system, geological processes such as weather cycling have scattered the externally delivered water all around the globe. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when MESSENGER detected volatiles on the sun-scorched world. Volatiles are chemicals that can jump between solid and gas phases in a short temperature change. Mercury already proved it sheltered water, a volatile, but MESSENGER found others such as sulfur, potassium, and chlorine that easily vaporize at moderately high temperatures. These volatiles are distributed all across the surface of the planet. For its size, Mercury contains as much volatile content as other terrestrial planets in the solar system that are farther from the Sun and hence much colder. Where the volatiles come from and how Mercury has retained them are still matters of scientific debate. Some researchers think that the volatiles came from underground relatively recently, while others think the chemicals have persisted on the surface since an embryonic Mercury condensed from its protoplanetary disk. The volatiles on Mercury raise questions. For example, if planets that edge up against their stars have volatiles, especially water, could these locales also be habitable? Well, it's possible that Mercury once held the ingredients for life. Indeed, Mercury has irregular depressions in the ground called hollows. Mariner 10 first glimpsed them in 1975. Then, MESSENGER photographed these shallow tracts at fine resolution. The depressions span from a few dozen feet to over a mile across, and they may be as deep as 120 feet. They look like the soft, airy insides of a sourdough loaf cut open. The hollows may be the doing of volatiles, scientists theorize. Since the atmosphereless Mercury has no rain or wind to carve the land, surface features like hollows can only be formed from other processes, such as the ground leaking volatiles into space. Hollows are relatively young formations, about 100,000 years old on average, compared with some 4 billion-year-old impact craters on Mercury. Scientists think hollows are still forming today, and hollows are unique to Mercury. No other celestial body in the solar system seems to present similar pockmarks. In recent years, scientists have identified other structural formations on Mercury, chaotic terrains, jumbled ridges that look like a failed game of Jenga, cut up vast swaths of the land. Some researchers think the chaotic terrains are the result of the ground wafting volatiles until it loses structural integrity and collapses. Other scientists think that chaotic terrains form after ripples from an asteroid impact encircle the planet and meet on the opposite side of the globe. In addition, lava on the planet. Mariner 10, first glimpsed and then Messenger later confirmed that glossy plains spread across Mercury's surface. Each plane suggests pooled lava smoothed over older craters and ridges. Researchers think that magmatic volcanism halted on Mercury anywhere between 1 billion to 3.5 billion years ago, due to planetary cooling and contraction that plugged up the magma's escape routes. Mercury has also shown signs of another kind of volcanism, explosions. If streaming lava is like a runny nose, then explosions are the volcanic equivalent of a sneeze. Irregular pits several miles across and more than 2 miles deep hint at ancient pyroclastic volcanoes that self-destructed. Scattered around these pits are deposits that researchers think are ejecta from the explosion. These types of volcanic bursts are probably caused by volatiles underground. When these buried chemicals rise to the surface, they expand in volume. Eventually, the pressure buildup of gases causes the volcano to pop, like an overfilled balloon. But volatiles, a chemical category that includes water, are essential for sparking and supporting life as we know it here on Earth. So, their potential presence on Mercury is an intriguing development. Astronomers now speculate that beneath the scorching surface of Mercury, the closest dwarf planet to the Sun, there could be signs of life. But how could volatiles, which are essential to life here on Earth, survive on a planet whose daytime temperatures soar to 430 degrees Celsius and drop to minus 180 degrees Celsius at night? Alexis P. Rodriguez, a researcher at the Planetary Science Institute in Arizona, explained that while the planet's surface swings wildly between temperature extremes, just below the surface, temperatures are milder. In the words of Rodriguez, it's likely that there was some sort of water that formed in part of Mercury's crust. But the team cannot yet tell exactly what volatiles were present when the planet's surface broke apart. While the mystery remains, a completely unexpected discovery made by NASA's Messenger spacecraft revealed that a 10-mile-thick diamond mantle may lie beneath the crust of Mercury. While instances of such valuable encrustation might sound tantalizing, turning these precious stones into fashionable jewelry remains an impossibility due to their inaccessible location deep within the planet. However, these gems could hold the key to unraveling some of the big unanswered questions circling around Mercury composition and its rather curious magnetic field. These diamonds may facilitate heat transfer between the core and mantle, thereby creating temperature differences and causing liquid iron to circulate, a process that would kickstart the creation of a magnetic field. The discovery of a potential diamond layer within Mercury opens new avenues for planetary research and composition studies, not only of Mercury, but also of other celestial bodies. Understanding the unique geological characteristics of Mercury could provide deeper insight into the formation and evolution of the solar system. The new discovery also prompts a reconsideration of the processes involved in planetary formation. Diamonds are typically associated with high-pressure environments, suggesting that similar conditions may exist in other distant rocky exoplanets and moons within our solar system. Studying extreme planetary conditions can reveal not only the composition of these bodies, but also the historical processes that formed them, leading to a more comprehensive understanding of geology across the cosmos. The potential discovery casts a new light on the evolution of carbon-rich exoplanets. The process that led to the formation of a diamond layer on Mercury could also be at play on other planets, possibly leaving similar traces. The arrival of the Bepicolombo spacecraft, a joint mission of the European Space Agency and the Japan Aerospace Exploration Agency, in 2025 will provide better opportunities to delve deeper into this intriguing discovery. Bepicolombo, was launched in 2018 on a complex trajectory to the solar system's innermost planet. The ESA reports that the spacecraft's thrusters have lost some power. Bepi Colombo's mission is to complete a comprehensive investigation of Mercury's magnetosphere, magnetic field, and internal and external structure. But traveling around in the inner solar system is complicated, and the Bepi Colombo spacecraft will use more energy getting to Mercury than it takes to get to Pluto. The spacecraft will perform 9 planetary flybys before reaching its destination at the end of 2025. Bepi Colombo has already performed 1 gravity assist at Earth, 2 at Venus, and 5 at Mercury. It'll perform 1 more at Mercury in January 2025. The Mercury Transfer Module, or MTM, is the part of the spacecraft that delivers a pair of orbiters to Mercury. On April 26th, as the spacecraft was about to execute its next maneuver, the MTM didn't deliver enough electrical power to its thrusters. A team working on it restored the thrust back to 90% on May 7th. But the MTM still isn't deliver enough electricity to get back to 100% thrust. Despite the power problems, the spacecraft is on track to complete its final Mercury flyby. A team is working to maintain the current power level and to understand how the diminished thrust will affect future maneuvers. They're also working on restoring full power to the thrusters. To facilitate this, the mission's flight control team at the European Space Operations Center in Darmstadt, Germany, has arranged additional ground station passes. Bepi Colombo employs a solar electric propulsion system. 2 15-meter-long solar cells gather energy and deliver it to 4 ion thrusters that use xenon propellant. The thrusters are mounted on gimbals, making them aimable. Bepi Colombo consists of 3 separate spacecraft. The Mercury Transfer Module is kind of like a tugboat, delivering 2 separate orbiters to Mercury. One of the orbiters is the Mercury Planetary Orbiter, and it carries 11 scientific instruments, including cameras, several spectrometers, a magnetometer, and others. The other one is the Mercury Magnetospheric Orbiter, largely built by JAXA. It carries 5 groups of instruments, including one group that will study the plasma and neutral particles from the planet, its magnetosphere, and the solar wind. While waiting for the first data obtained by Bepi Colombo, scientists also put their hope in another tool, the James Webb Space Telescope. The Supreme Space Telescope comes with significant advantages over any previous mission. First and foremost is its size. James Webb features a 21.7-foot mirror composed of 18 gold-plated hexagonal segments. This colossus gathers more than 6 times as much light as the Hubble Space Telescope's 7.8-foot mirror, so it can record light from objects 6 times faster than its predecessor. But Webb's sensitivity to infrared light is the real game changer. The Space Telescope can view wavelengths from the red end of the visible spectrum to the mid-infrared. Hubble's optics are optimized to record radiation from the ultraviolet to the near-infrared, with the majority of its sensitivity centered on visible light. Perhaps surprisingly, in its intended infrared domain, James Webb generally won't resolve finer details than Hubble achieves in optical light. Although resolution increases with mirror size, it also diminishes with wavelength. Observing in the infrared allows astronomers to see galaxies that existed less than 1 billion years after the Big Bang. These distant objects emit ultraviolet and visible light, but the expansion of the universe shifts this radiation to longer infrared wavelengths. Peering into the infrared is the only way to observe these young galaxies from Earth's vicinity. The same holds true for newly forming stars. The dust that envelops infant suns scatters visible light, hiding what lies within from our eyes, but it lets infrared radiation largely pass through. Despite its focus on distant galaxies and star formation, James Webb is an all-purpose observatory. Its powerful infrared eye sees details in solar system objects beyond the reach of conventional telescopes. Early observations include studying cloud belts on the gas and ice giant planets, tracking cloud formations on Saturn's largest moon, Titan, exploring Pluto's climate, and probing many of the smaller asteroids and trans-Neptunian objects that populate the outer solar system. The telescope even observed the asteroid moonlet Dimorphos in September, when NASA's double asteroid redirection test slammed into it. The impact slightly changed the object's orbit around its parent body, Didymos, helping the space agency assess its ability to alter the course of potentially hazardous asteroids that could cross Earth's path. Thus, it's not far-fetched to think of the Space Observatory can take a closer look at Mercury, unlocking the subterranean secrets of the closest planet to the Sun. In the latest observation, using James Webb, astronomers discovered that Ariel, a moon of Uranus, could be hiding in a buried liquid water ocean. The discovery could supply an answer to a mystery surrounding this Uranian moon that has perplexed scientists. The fact Ariel's surface is covered with a significant amount of carbon dioxide ice. This is puzzling because at the distance, Uranus and its moons exist from the Sun, 20 times further out from the Sun than Earth. Carbon dioxide turns to gas and is lost to space. This means some process must refresh the carbon dioxide at the surface of Ariel. Previous theories have suggested this happens as a result of interactions between Ariel's surface and charged particles trapped in Uranus's magnetosphere that provide ionizing radiation, breaking down molecules and leaving carbon dioxide, a process called radiolysis. However, new evidence from the Webb telescope suggests the source of this carbon dioxide could come not from outside Ariel, but from its interior, possibly from a buried subsurface ocean. Because chemical elements and molecules absorb and emit light at characteristic wavelengths, they leave individual fingerprints on spectra. The team behind this discovery used James Webb to gather spectra of light from Ariel, which helped them paint a picture of the chemical makeup of the Uranian moon. Comparing this to simulated spectra from a chemical mix in the lab here on Earth revealed to the team that Ariel has some of the most carbon dioxide-rich deposits in the solar system. Not only did this add an extra 0.4 inches of thickness to the ice on the side of the tidally locked Ariel that permanently faces away from Uranus, but it also revealed clear deposits of carbon monoxide for the first time. As team leader Richard Cartwright from the Johns Hopkins Applied Physics Laboratory, or APL, said in a statement, "It just shouldn't be there. You've got to get down to 30 kelvins, minus 405 degrees Fahrenheit, before carbon monoxide's stable. The carbon monoxide would have to be actively replenished, no question. That's because Ariel's surface temperature is, on average, around 18 degrees Celsius warmer than this key temperature." Cartwright acknowledges that radiolysis could account for some of this replenishment. However, observations from Voyager 2's 1986 flyby of Uranus and its moons and other recent findings have suggested that the interactions behind radiolysis could be limited because Uranus's magnetic field axis and the orbital plane of its moons are offset from each other by about 58 degrees. That means that the majority of the carbon-oxygen compounds seen on Ariel's surface could be created by chemical processes in a liquid water ocean trapped under ice on Ariel. Once created in the seep water ocean of Ariel, these carbon oxides could then escape through cracks in the icy shell of the Uranian moon, or could even be explosively ejected by powerful eruptive plumes. Scientists have suspected for some time that the cracked and scarred surface of Ariel may indicate the presence of active cryovolcanoes, volcanoes that erupt plumes of icy slush rather than lava. These plumes could be so powerful that they launch material into Uranus's magnetic field. The majority of the cracks and grooves seen on the surface of Ariel are located on the side of the moon that faces away from Uranus. If carbon dioxide and carbon monoxide are leaking from these features to the surface of the Uranian moon, this could explain why these compounds are found in greater abundance on this trailing side of the icy body. In addition, James Webb also picked up more chemical evidence of a subsurface liquid water ocean. Spectral analysis hinted at the presence of carbonate minerals, salts created when rock meets and interacts with liquid water. As Cartwright explained, if our interpretation of that carbonate feature is correct, then that is a pretty big result because it means it had to form in the interior. That's something we absolutely need to confirm, either through future observations, modeling, or some combination of techniques. Uranus and its moons haven't been visited by a spacecraft since Voyager 2 almost 4 decades ago, and this wasn't even the spacecraft's primary mission. In 2023, the Planetary Science and Astrobiology Decadal Survey emphasized the need to prioritize a dedicated mission to the Uranian system. Cartwright believes such a mission would present an opportunity to collect valuable information about Uranus and Neptune, the solar system's other ice giant. Such a mission could also deliver vital data about the other potentially ocean-bearing moons of these systems. This information could then be applied to extrasolar planets or exoplanets beyond the solar system. As team member and NASA Applied Physics Laboratory scientist Ian Cohen said, all these new insights underscore how compelling the Uranian system is, whether it's to unlock the keys to how the solar system formed, better understand the planet's complex magnetosphere, or determine whether these moons are potential ocean worlds. Many of us in the planetary science community are really looking forward to a future mission to explore Uranus. In another remarkable study made by James Webb, astronomers have investigated a new super-Jupiter planet that is one of the coldest worlds ever seen outside the solar system. The exoplanet is located in the triple star system Epsilon Indi, which sits around 12 light-years away. The planet is designated Eps Ind Ab and has a mass around 6 times that of Jupiter. It orbits its red dwarf parent star at a distance similar to that between Neptune and the Sun. This gives the world a surface temperature of around 0 degrees Celsius and means one orbit of the planet takes around 200 Earth years. The Webb telescope was able to image the exoplanet using the sensitive infrared capabilities of the mid-infrared instrument. The investigation of Eps Ind Ab could help astronomers better understand the evolution of gas giant planets and their systems. This is the first time that the powerful space telescope has been able to image an exoplanet that wasn't previously imaged from the ground. Eps Ind Ab is also the coldest exoplanet James Webb has been able to study thus far. That's why scientists were excited when we realized we had imaged this new planet. To their surprise, the bright spot that appeared in our MIRI images did not match the position we were expecting for the planet. They added that previous studies had correctly identified a planet in this system, but had underestimated the super-Jupiter gas giant's mass and orbital separation. The team was able to correct this with the help of James Webb. The crew determined the planet has a highly elliptical, or flattened, orbit that, at its closest, brings it to a distance about 20 times the distance between Earth and the Sun. At the furthest point in its orbit, Eps Ind Ab is 50 times further away from its parent star than the average distance between Earth and the Sun. The world's parent star, a red dwarf named Eps Ind A, has 2 stellar companions. Both are brown dwarfs, or failed stars, named as such because they're objects that form like stars but can't gather enough mass to trigger nuclear fusion processes in their core that define what a main sequence star is. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. The solar system, our cosmic neighborhood, has intrigued and captivated human curiosity for centuries. Within its vast expanse, from the scorching heat of the sun to the icy reaches of the Kuiper Belt, lie numerous mysteries that challenge our understanding of planetary formation, evolution, and the potential for life beyond Earth. One of the earliest scientific discoveries about it was also the most significant. The Earth was not the center of the universe, but orbited the Sun. In the centuries since Copernicus redrew the cosmic map, scientists have traveled closer to the heart of the solar system, first with telescopes, then with satellites and spacecraft. They learned about the nuclear fusion that powers our star and countless others and, with the discovery of exoplanets, realized that many stars could be someone else's sun. Today, our understanding of the Sun and its subtle mechanisms is more sophisticated than ever before, but it remains incomplete. When you look toward the edge of the solar system, you'll find a vast, dark place in which mysterious entities can easily hide. As a result, researchers have had a field day cataloging all the things that could be lurking out there. From a massive ninth planet and a second Kuiper belt to interstellar visitors and mini black holes, here are weird objects that could be lurking in the darkness out there. Number 1. Planet 9. The largest and most controversial object that could be lurking in our cosmic neighborhood is a hypothetical ninth planet dwelling far beyond the other known solar system worlds, which researchers have creatively nicknamed Planet 9. Scientists first proposed Planet 9 in 2016 to explain the eccentric orbits of several large objects in and around the Kuiper belt, a massive ring of asteroids and other rocky objects that circle the Sun beyond the orbit of Neptune. Some researchers believe these objects are being gravitationally tugged by a massive, unknown world beyond the Kuiper belt. But despite finding even more of these objects in recent years, the actual planet has evaded detection so far. If it does exist, Planet 9 is likely an icy gas giant around 7 times more massive than Earth, which would make it the 5th largest planet in the solar system. However, the planet could be extremely far away, possibly orbiting our Sun once every 10,000 years, which means it would be very faint and extremely hard to spot. Researchers have narrowed down the area where Planet 9 could be hiding, but are limited by the strength of the telescopes currently available. However, with new state-of-the-art telescopes soon coming online, it could be discovered within the next few years. Number 2. Baby black holes. Not everyone believes that Planet 9 is responsible for the orbital anomalies of Kuiper belt objects. Other scientists believe that something equally hard to spot could be gravitationally tugging on these distant space rocks, a mini black hole. Researchers argue that a black hole that's around the size of a moon or planet could exert the same gravitational force as the supposed Planet 9. Black holes of this size are theoretically possible, but have never been observed, which makes this idea somewhat controversial. To prove this theory, researchers would probably need to detect Hawking radiation coming from the black hole, or watch something fall beyond its event horizon. But even if a baby black hole is not masquerading as Planet 9, other researchers believe there could be even smaller primordial black holes in the outer solar system, and that these super small singularities could be making some planets and moons wobble. Number 3. Captured alien worlds. Some researchers believe there could be more hidden worlds, other than Planet 9, in the outer reaches of the solar system. But unlike Planet 9, these hypothetical planets, known as rogue planets, may not have originated in our neck of the woods. Instead, they would be castaways from distant stars that may have been pulled in by the Sun after drifting in interstellar space for eons. Scientists have already detected hundreds of rogue planets zooming across the Milky Way. However, in 2023, researchers proposed that a rogue planet could be lurking near the solar system's edge, even further out than Planet 9. And if that wasn't crazy enough, a 2024 paper also suggested that there is space for up to 5 Earth-size rogue planets toward the edge of our cosmic neighborhood. Number 4. Second Kuiper belt. the Kuiper Belt could play a key role in detecting hidden worlds within the solar system, but it may also be hiding a secret of its own, a twin. In 2023, researchers announced the potential discovery of a dozen new rocky objects lurking beyond the Kuiper Belt. These hefty space rocks, which are likely all asteroids, are located around 10 astronomical units, that is 10 times further than the distance between Earth and the Sun from the majority of the Kuiper Belt, suggesting they could belong to a second, smaller belt of asteroids. However, other surveys have failed to identify any more of these extra Kuiper Belt objects, which has left this theory in limbo for now. Number 5. More dwarf planets. After fully fledged worlds and missing asteroid belts, the next largest objects that could be hiding under our noses are dwarf planets. Large space rocks that are big enough to be gravitationally rounded, like planets, but not big enough to completely clear their orbital pathway of debris. The solar system harbors 5 known dwarf planets: Ceres, Haumea, Eris, Makemake, and the exoplanet Pluto. Other candidates such as Gonggong, Quaoar, and Sedna are not officially recognized as dwarf planets, but are often referred to as such by astronomers. All of these mini-worlds lie within the Kuiper Belt or beyond, apart from Ceres, which is located in the asteroid belt between Mars and Jupiter. But as we have already seen, there are plenty of places for objects to hide in the outer solar system. Some estimates suggest there could be dozens or even up to 100 dwarf planets still waiting to be discovered. Until recently, researchers believed that the dwarf planets were mostly geologically dead, except for Pluto, which has an icy supervolcano. However, new data collected by the James Webb Space Telescope revealed that Eris and Makemake may also be geologically active, which increases the chances they or other future dwarf planets could harbor alien life. Number 6. Volcanic comets. Far beyond the Kuiper Belt lies a gigantic reservoir of comets known as the Oort cloud, which extends to around 1,000 astronomical units from the Sun. A very small percentage of these icy objects are what researchers refer to as cryovolcanoes, or cold volcanoes, that shoot dust and frozen gas into space when they erupt. Cryovolcanic comets only erupt near the Sun when solar radiation causes intense pressure to build up within their outer shells, or nuclei, eventually triggering explosive outbursts. However, most comets have highly elliptical orbits, meaning they spend a majority of their orbits floating in the outer solar system before sweeping into the inner solar system every few decades or centuries. This makes it hard to spot which ones are cryovolcanic. For example, Comet 12P Ponce-Brooks, also known as the Devil Comet, made its closest approach to the Sun for around 71 years when it slingshotted around our home star in April 2024. Since June 2023, when the comet began its dive bomb into the inner solar system, the comet has been spotted erupting multiple times. But for the preceding 69 years, astronomers didn't see it explode once. As a result, astronomers suspect that many more cryovolcanic comets are hiding in plain sight within the Oort cloud, and that we'll only identify them when they eventually approach the Sun. Number 7. Interstellar visitors. In addition to suspected rogue planets, the Sun's gravitational might is also capable of pulling in other free-floating objects from interstellar space. However, unlike the supposed captured worlds, a majority of these objects likely pass through our cosmic neighborhood and never return. Astronomers have already spotted 2 confirmed interstellar objects: Oumuamua, an oblong object that made headlines in 2017 after some researchers mistakenly suggested that it could be an alien probe, and Comet 2I Borisov, which was spotted in 2019 as it sailed through the solar system. Other researchers suspect that a tiny meteor that exploded over Earth in 2014 was also an interstellar interloper. Given the tiny number of confirmed sightings, you'd be forgiven for thinking that interstellar objects are rare. However, some researchers estimate that there are between 1,000 and 10,000 of these objects in the solar system at any one time. Some researchers have proposed the creation of special interstellar interceptor spacecraft that could be stashed in orbit around Earth so that scientists can quickly chase and study new objects as soon as they are discovered. But at present, there are no official plans for such spacecraft. Number 8. Killer asteroids. The final objects on this list are the most dangerous, but thankfully, they are among the least likely to be found. The inner solar system is filled with potentially hazardous asteroids, which orbit the Sun close enough to Earth to be considered a threat to our planet, even though most will never get anywhere near us. These perilous space rocks can range in size from city killers that could wipe out large population centers to planet killers, like the one that wiped out the dinosaurs. Similar massive rocks reside in the Kuiper Belt and beyond. However, unlike comets, asteroids don't usually migrate in and out of the inner solar system, meaning these rocks do not pose much threat to us. But this doesn't mean it's impossible. If a massive asteroid did venture toward Earth, it could also be obscured by the glare of the Sun, depending on its position, which could give us very little warning before it snuck up on us. Scientists calculate that potentially hazardous asteroids pose no threat to Earth for at least 1,000 years. However, that calculation is based solely on the space rocks we know about. As we push more robots into space, improve our observational capabilities, and begin to experience space for ourselves, we learn more and more about the nature of where we come from as well as what really hiding out there. But even with our advancing knowledge, we would be naive to think we have all the answers. So much still needs to be uncovered. Here are the most perplexing conundrums our solar system has thrown at us. What killed Venus? Venus is only slightly smaller than the Earth, and so has enjoyed billions of years of a warm heart. But for this planet, sometimes called Earth's sister, that heat has betrayed it. That planet is now wrapped in suffocating layers of a poisonous atmosphere made of carbon dioxide and sulfuric acid. The pressures on the surface reach almost 100 times the air pressure at Earth's sea level. The average temperatures are over 700 degrees Fahrenheit, more than hot enough to melt lead, while the deepest valleys see records of over 900 degrees. If Venus is indeed Earth's sister, she's a twisted one. Like Mars, we suspect that Venus also once hosted a thinner, balmier atmosphere and a surface replete with liquid water oceans. The reasoning here is a little more tenuous than for Mars, where we can literally see the evidence for water before our very eyes. But the thinking is that both Venus and Earth formed in a roughly similar fashion, in roughly the same orbits with roughly the same material. Thus, we should have been born with roughly the same amount of water. Like Earth, most of that water would have been chemically bound up in rock, buried deep in the mantle. But some of it may have leached to the surface or been delivered by hosts of water-rich comets shortly after formation, building up a supply on the surface, once again stabilized by a thick atmosphere. What doomed Venus was not any fault of its own, but our own treacherous sun. As stars age, they gradually brighten. Day by day, it's imperceptible. But over the course of millions of years, it completely changes the character of a star. Billions of years ago, our sun's habitable zone was shifted inwards compared to where it rests now, but with increased brightness comes increased heat, and that habitable zone steadily creeps outwards over time. Did Venus ever host life? We doubt we'll ever know, given the excruciating temperatures on the surface that make exploration nearly impossible. But it's likely that it had water and a rich atmosphere. The basic ingredients were there. But if life did gain a foothold, it did not last long. As our sun aged, Venus got warmer and warmer. On a warmer planet, more water exists as vapor in the atmosphere than as liquid on the surface. At first, the changes were small, with nothing more than a higher dew point to mark the inexorable path to destruction. But at some point in the past, we are not sure exactly when, Venus reached a tipping point. With too much water vapor, the atmosphere of Venus became too good at trapping the heat radiating from the surface. That radiation could not penetrate the haze and make into space, but instead was ensnared within the atmosphere itself, heating it up. What came next was, at least, mercifully quick. Venus entered a feedback loop, dumping more heat into the atmosphere, which boiled the oceans into more vapor, which increased the temperatures, and so on. First, the shallow lakes and streams were gone. Then came the deeper oceans, until every scrap of water was blowing in the winds of the atmosphere. With its proximity to the ever-brightening sun, the water vapor did not last long. Solar radiation pummeled it, disassociating its chemical bonds and sending the oxygen and hydrogen flying away, joining a grim procession beyond our solar system. If Venus had plate tectonics like the Earth, then this is where that process came to end. With no water to act a lubricant, the great slow grinding of the plates seized up, locking the crust in place. This constant churning acts as a natural sink for carbon. The carbon dioxide binds to rocks which get pulled deep into the mantle, preventing too much carbon from building up in the atmosphere. But without the cleansing effect of plate tectonics, carbon dioxide levels rose to dangerous heights, its own ability to absorb radiation from the surface, choking off any remaining hope for rescuing the planet. Eventually, the atmosphere would pile upon itself until it reached its present swollen size. As our sun aged, Venus strangled itself. Venus is not alone in sharing that fate, for the sun has not yet reached its final days. It continues to brighten, bringing more warmth to the solar system day by day, its habitable zone steadily inching outwards with every passing year. At some point, approximately 500 million years from now, Venus will not be alone. The Earth's oceans will boil, our continents will halt their ancient motion, and we will finally be twins with our sister, dead, lifeless, and strangling on our own bloated atmosphere. Where the heck did the moon come from? Before the moon landings, scientists thought they knew how the moon formed. The prevailing theory was that it formed a lot like the planets did, bits of material left over from the formation of the sun, lumping together. But then, Apollo astronauts brought samples back from the lunar surface, and those rocks told a totally different story. The Apollo evidence all pointed to the moon forming from a large impact. The age of the rock samples indicated that the moon formed around 60 million years after the solar system began to form. The type and composition of the samples showed that the moon had been molten during its formation and was covered with a deep ocean of magma for tens of millions to hundreds of millions of years, an environment that would occur in the aftermath of an intensely energetic impact. Lunar rocks were found to contain only small amounts of elements that vaporize when heated, further indicating the moon could have formed in a high-energy impact that let those elements escape. Perhaps most importantly, the rock samples indicated that the moon was once a part of Earth. Basaltic rocks from the moon's mantle have striking similarities to basaltic rocks from Earth's mantle. The oxygen isotopes and other elements sealed into the specimens matched those of Earth rocks too precisely for the similarities to be a coincidence. Spread magma ocean that was quite deep, from hundreds to thousands of kilometers. And with humanity's return to the moon through the Artemis program, scientists expect a flood of new information that will help us hone in on a single formation scenario. In the meantime, scientists continue to study existing samples and other information they have now, such as information from lunar orbiters and the growing body of knowledge on planetary formation, to construct computer models that help us understand how the collision might have happened and how it could have resulted in the moon and Earth as we see them today. The models account for factors like the strength of the colliding objects, the friction between the components, the density of the components, and how materials behave under different temperatures and pressures. Today's advanced computer models can provide a number of very specific outcomes based on variables like these. How did Uranus end up on its side? Uranus is just plain weird, and one of the weirdest things about it is its tilt. Uranus has the largest tilt in the solar system at 98 degrees, which means it spins almost perfectly perpendicular to the direction of its orbit. Astronomers have long suspected that a series of giant impacts early in the planet's formation did the job of flipping Uranus on its side. But new research suggests a much less violent cause: a satellite of Uranus that wandered away. All the planets of the solar system have orbital tilts less than 30 degrees, except Uranus. The whole Uranus system is flipped onto its side, affecting not just the planet's rotation, but also its rings and moons too, which orbit around the planet perpendicular to the planet's motion around the sun. The odd tilt of Uranus is especially weird considering that the neighboring ice giant, Neptune, has a normal tilt despite the two likely sharing similar formation histories. So what went wrong for Uranus? Astronomers have long suspected that at least one giant impact occurred when Uranus was forming. It's easy enough to imagine. The right collision at the right time would deliver enough energy to push Uranus over while it was still in its protoplanetary stage, and the planet never picked itself back up before forming its system of planets and moons. And scientists have some evidence to support this picture. The solar system was a rather violent place in its youth, so there are plenty of large rocks around to wreak havoc. And Neptune does display slight differences, such as a different temperature and a set of moons with different characteristics, indicating the two planets experienced distinct conditions at some point in their formation. But the impact hypothesis has weaknesses too. There wasn't just one large rock whizzing around the early solar system looking for an unlucky target. There were many. All the planets, especially the outer ones, likely suffered many collisions during their formation. Even the inner planets weren't spared. Earth got smacked by a Mars-sized protoplanet early on, forming the Moon. So if Uranus got hit hard enough to tip it over, why didn't the other planets? Jupiter and Saturn eventually developed thick clouds of gas, which could, over time, have gotten them upright again. But Neptune had a similar history to Uranus, and despite their small differences, the two ice giants are extremely alike. They have similar atmospheres, both have tangled magnetic fields, and have similar sizes, masses, and spin rates. We're left with a dilemma. Perhaps poor Uranus was just extremely unlucky, and there are simulations that support the idea of just the right impact tilting the world. But pure luck doesn't really satisfy the typical astronomer. We should exhaust all the other options before resorting to it. So perhaps the answer doesn't have anything to do with impacts. Perhaps it has to do with moons, as a team of scientists propose in a new paper accepted for publication in the journal Astronomy and Astrophysics, and posted to the preprint site, thearchidev.org. According to the paper, Uranus could have been born with or quickly captured a massive moon, and if the moon was big enough, it could have started playing games with the planet's spin. Uranus likely started out with a random but small tilt. Over time, that tilt will precess, as astronomers call it, with the direction of the planet's rotation, wobbling like a gigantic top. Earth does the same thing. Usually, a moon doesn't care about its planet's precession of tilt, but it's possible for a moon to get locked into a resonance pattern, in which the length of time needed to precess matches up with a whole number of orbits of the moon. This resonance allows the gravitational force of the moon to gently tug on the planet, reinforcing the precession. It's like an invisible string attached to the top of the planet. Over the course of millions of years, that tilt gets worse and worse. As this goes on, the moon's orbit would creep steadily closer to the planet. The researchers found that if Uranus once had a large enough moon, it would, within a few 100 million years, be capable of pulling the planet's tilt over 80 degrees. To finish the job, the satellite would then crash into Uranus, locking the planet's tilt at its present value. This scenario would explain why Uranus is so unique. It just had a large enough moon, which is common enough, that slipped into resonance. Not so common that we should expect the same to happen to Neptune. And then it all went sideways from here. How do we know the Oort cloud even exists? The Oort cloud is a vast reservoir of icy bodies, numbered in their billions, perhaps trillions, that make up a ghostly shell around the entire solar system. Though it has never actually been observed, this spherical region is named the Oort cloud, after Jan Oort, the Dutch astronomer who suggested its existence in 1950. Oort did so to explain the appearance of comets with orbital periods of many thousands of years, reviving a similar idea that had been proposed by Estonian astronomer Ernst Öpik 18 years earlier. But where is the Oort cloud? Frankly, it's a tricky task, attempting to measure distance in space. But it has been suggested that the Oort cloud begins at around a light-year's distance from the Sun, and may stretch as far as a third of the way to the next nearest star, Proxima Centauri. It is a region filled with frozen fragments of water, ammonia, and methane left over from the formation of the solar system, and, though the fragments are fairly insubstantial individually, together they could add up to several times the mass of the Earth. Some of the most impressive long-period and non-periodic comets are thought to have started their journeys here, after being dislodged by some unknown event. The Oort cloud is thought to have sent us comets C1996 B2 Hyakutake, C2011 L4 Pan-STARRS, and C2012 S1 ISON. But it is not the only source of them. Short-period comets are thought to come from somewhere much closer, a region beyond Neptune called the Kuiper Belt, and the area just beyond it known as the Scattered Disk. We don't have any observations to confirm whether the Oort cloud exists or not, and it is too far to study with space probes. Voyager 1, which NASA has crossed into interstellar space, will not reach it for hundreds of years, by which time it will be long past its useful life. Even New Horizons, which has reached the Kuiper Belt, will be unable to help us. But the theory that the cloud exists is a neat one, explaining how these icy solar system leftovers come to grace our skies. After all, the Oort cloud appears to be out there, but we cannot directly observe it. So, in my books, that is the biggest mystery in the outermost region of our solar system. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.